Here is the first example. We have to find the volume of the right circular cylinder with maximum value that can be inscribed in a sphere with radius r. And here is a really good picture of, as you can see, the cylinder in the sphere. What we are going to do, we're going to insert this triangle, which is really in the center of the cross section, in the middle. So I want to show you really that even though I gave you this very fancy drawing, really what I need is only the center cross section. This is obviously r. It's the radius of the sphere. And I also need this one because this is the radius of the cylinder. So we are going to label this in small r. And this is the height of the cylinder. Because this is the more important issue, I'm going kind of to take it out. So I'm going really just to relate to this one. And I already see connection here between everything. It's Pythagorean theorem. If you look at the triangle, you can see that capital R to the power of 2 equals small r to the power of 2 plus half of the height to the power of 2. So this is the equation. I would like to recall that the sphere has radius capital R. It means that capital R is a constant. It's replacing some given number. It's a symbol and we do not have to find it. We only have to find the small r and the h. So the function to be maximized is the volume of the cylinder. What is the volume of the cylinder? It is pi r to the power of 2 times the height, which is h. We need now one variable function, so we are going to use the equation as usual. The question is, which of those variables you want to replace, and I think in this case it's pretty trivial. I'm going, obviously, to replace r to the power of 2 because it's already squared and I don't need to use radicals. So let's replace that, and we're getting this one. Let's simplify. We get that. Let's think now about possible values for the variable. So the variable is now h. And if you pay attention, h cannot exceed 2 times the radius of the sphere. But also, it cannot also be less than 0. So definitely, h is greater or equals to 0 or less or equal to 2r. So here I'm going to use, as you can see, a very simple picture. So according to what we got before, we know that h over 2 cannot exceed r, because I recall h was less or equals to r, so h over 2 is less or equals to r. So now let's find the critical numbers on the interval 0 and 2r, including 0 and 2r. So we are differentiating v, and we get that. Okay, very easy to solve to h, as you can see, because I can just write it like this. Everything is positive here. So I can do that. I don't need to write even as product of terms because I don't care about h being negative. And as you can see, we can take away those pi's here. Okay, and multiply both sides by 4 over 3. And we get that which means that h equals actually just the plus, obviously, 2 over square root of 3 times r. So this is the only critical number. So now we are going to do a chart because this is a closed interval problem to show for absolute maximum. So here is the chart. Okay, so first of all, let's substitute the first value of h. So this is just algebra. We'll do the algebra here. Common denominator. And we get 4 pi over 3 times square root of 3 times r to the power of 3. I would like to recall that r is a constant. This is the radius of the sphere. So we get that. At 0, we get 0. And let's see what do we get in capital R. Okay, please pay attention. What is h? H is 2 times r. Okay. And we get this expression, which is also 0. It's making a lot of sense. If you think about the height, if there is no height, then obviously there is no volume for the cylinder. And if you take everything for the height, then there is no radius to the cylinder. So it just makes sense. Okay, so now we just compare those numbers, which is very easy because 2 of them are zeros, and we get that this is the absolute maximum. So here's the answer. The maximum possible volume is 4 pi over 3 times square root of 3 times r to the power of 3 cubic units. Here is our last example. Find the volume of the cone with maximum volume that can be inscribed in the lower half of a sphere with radius r, as in the picture below. So this is a big help because we don't need a very sophisticated picture here, but we're still going to draw. We're going to simplify everything by again going to the center, and this is the cross section exactly in the center. And from here we can find out using this triangle that the connection between h and capital R and small r is that. And also this is the equation because this connects between all those variables, and the variables are just h and little r because capital R is a fixed number, is the given radius of the sphere. So what is the volume? So it is the area of the base, which is pi r to the power of 2 times the height h over 3. And we need now to simplify by eliminating one variable. We can eliminate the h or we can eliminate the r to the power of 2. I will definitely eliminate r to the power of 2 because from the equation it's very easy to see what is r to the power of 2. R to the power of 2 is just capital R to the power of 2 minus h to the power of 2. And when we substitute this, we get this. And we simplify, and we get that this is the main function. What are the possible values for the variable? If you look at the picture, you can realize that h has to be greater or equals to 0, but also, because it's in the lower half of a sphere, it cannot exceed the radius of the sphere. So h is greater or equals to 0 and less or equals to r. So let's find out the critical numbers on the interval 0 and capital R. The derivative is very simple now because this is just a polynomial. I would just like to note that I also was doing this exercise with eliminating h, and everything was very complicated in the algebraic sense. So it's really very important to know which one to eliminate. Okay, so I get this, and I want like this to be 0, obviously, so we are getting that r to the power of 2 equals 3h to the power of 2, and that's why h is r over radical of 3. Because h has to be positive, I'm not concerning about other things, and I can actually do that because everything here is positive. Now let's do the chart because it's a closed interval problem. So let's evaluate the volume at the critical. So we substitute r over radical 3, and we get that. So let's just simplify. We can distribute r cubed, and then we do a common denominator of 3 radical 3, and we get 3 minus 1, which is just 2 there. And we get that. At 0, we get 0. And when h equals r, we get this, which is also 0. So it's really very easy to realize that in this is the absolute maximum. And this is the answer. The maximum possible volume is 2 pi over 9 radical 3 times r cubed units cubed.